Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make general chemistry part of your day. This is another one-topic video. The topic here is resonance. And how do we explain some experimental data that seems to not match our Lewis dot structures? So for example, if I were to draw out carbonate, you would see one double bond and one single bond. I hope what you would predict is that the double bond will be stronger and shorter than the two single bonds. So if we were to get the actual crystal structure of this and be able to measure the bond length, you would expect to see two longer bonds and one shorter bond. Now, what if I were to tell you that all the bonds in carbonate are identical? And furthermore, what if I were to tell you all the bonds in carbonate are longer than a double and shorter than a single? They look like there's something in between. This would imply that this picture is totally wrong. So, at this point we have two options, right? When experimental data does not match theoretical data, we either have to throw out the whole theory or modify it. And as you know, if I'm teaching this, that means we're going to modify it. If we were just going to throw it out, why would I teach it in the first place? Other than, I suppose, to demonstrate that science changes over time. But I think you know science changes over time. Smartphones weren't the same 10 years ago. Things change. Ideas change. Practices change. Change is good. Embrace change. Okay. So, how do we explain that type of data? Without getting too far in the weeds for what we're doing and why, let's just get into the practice of it. So if I were to draw ozone out and draw the Lewis dot structure, you would see there's three oxygens in a line. One of them has a double bond, one of them has a single bond. Now my question is there any reason why the double bond should be on the left versus the double bond being on the right? And you might say, it's not even a different chemical, just change your piece of paper around and that's it. And that's true. But if we were to lock the nuclei in place, if we lock them in place, is there any reason the electron would want to flow to the left versus flowing to the right? And hopefully what you're saying is, one way is as good as another. And you'd be correct. Maybe not eloquent, but correct. And here is something called the Frank-Condon principle, is that the electrons move way faster than atoms. So the electrons can move around the molecule faster than the atom can adjust to that movement, making the bond shorter or longer depending on how many electrons are there. So going back to this idea of an orbital and the electrons blurring out a probability cloud, the electron blurs across the molecule or resonates from one piece of the molecule to another. This is called resonance. So if you want to imagine that this lone pair of electrons becomes part of a double bond here, and this double bond becomes part of a lone pair here, or the electrons just kind of flow to the left, we get this picture here. And if they flow back to the right, we get the picture up top. Now, of course, if we do this rapidly, billions of times in a second, what would the actual molecule look like? Well, it's not going to be able to adjust this double-single. You're going to end up with what essentially is a composite or an average, and that's going to describe the real molecule. So the average of all the resonance structures gives you the real molecule. So what's true in both these pictures? We got oxygen, 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 oxygen. Shape is maintained. There's a lone pair on the central atom. There's in both pictures two lone pairs and at least one bond. At least one bond and two lone pairs. So that's what's conserved. And then what we see is this kind of, I've put a dotted line in here, which is normally what you would show for where the electrons are resonating between the left and the right. And if we're looking at the average between those two pictures, we have no charge and a negative charge. So the average would be half a charge or a partial negative charge. This is positive, positive, so the average is positive 1. And the average between -1 and 0 is -0.5, so I'm going to put a negative partial there. And we can show the real distribution of what the molecule looks like. Okay, let's go back to this idea of bond order. I know I did briefly a while ago, and I said single bonds is 1, double bond is 2, triple bond is 3, and you probably thought boring. Why bother? Here's why. Now what I want to talk about is the bond order in a real ozone molecule. If I ask you anything about a molecule, never look at the individual resonance pictures. Always look at the average. You need to take the average of the pictures to talk about what's going on with the real chemical, with the real chemistry, with the real experimental results. It's the average of the pictures that matters. Each individual picture is not correct. They're only correct in totality if you put them all together. So, Now if I want to look at bond order, for those of you that don't like math, it's the total number of bonds between the two atoms divided by the total number of pictures. So what do I mean by this? Well, if I want to look at the left side, I have 1, 2, 3 sticks. I have 1, 2 pictures, or a bond order of 1.5. If I look at the right-hand side, I got 1, 2, 3 sticks divided by 2 pictures, a bond order of 1.5. Or the average of 1 and 2 is 1.5. Again, for those of you that don't like fractions and math, this will work. So what can we say about this bond? Well, we'd say both the left hand and the right hand side should be equal length and equal strength. They should both be stronger than a single bond, because that's bigger than 1, and they should be shorter than a single bond, because that's more of a connection. So that's how we can use that. So let's do another example. Let's say we want, and I want to just kind of make sure we can interpret these. So how do I know, and if you go back a slide in the upper right-hand corner, I had a little note there that I probably should have mentioned. You're going to have resonance when there's more than one equally good place to put the double bond. There's subtler forms of resonance, and I will leave that for your upper-level science courses. But as far as general chemistry goes, we're only going to move you have to keep everything connected. So if you don't have any double bonds, no resonance. But if you do have a double bond, look and see if there's more than one place you could place it. If there's more than one place you can put it, then you'll have resonance, and you need to put it in each of those spots. If there's 2 equally good spots, you get 2 structures. If there's 3, there's 3. If there's 4, there's 4. And if there's 5 or 6 combinations, I won't give you anything like that. There are some that exist in real life, though. You would have that many combinations. So let's take an example like this. Here is a correct Lewis dot structure for nitric acid. You can see the double bond is between this nitrogen and this oxygen. So it has a double bond. It's got same atoms around it. So this is one of these ones where, light bulb moment, ooh, we can probably have resonance here. So is there anywhere else I can put that double bond? So here's the key when you're doing resonance. You can't move any of the nuclei, i.e. you cannot move the letters. So if I have an N in the middle, I have an N in the middle. If I have an oxygen right above, I have an oxygen right above. If I have an H kinked over to the side, I got an H kinked to the side. Oxygen left, oxygen right. This cannot move in this. They have to stay connected. This has to be true. Now the question then is, where can I put the double bond? Can I put the double bond here? Does that look just like this? Oxygen on its own, oxygen on its own? Sure, why not? Double bond, boom, 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 bing, 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 bing. And we put it in brackets, and we use a little double-headed arrow, meaning it goes back and forth. My question is, can I put the double bond here? Would that be equally as good? And you might notice I didn't say, can I said, is it equally good? Well, oxygen likes to have 2 bonds. If we were to put a 3rd bond there, this is going to make oxygen unhappy. And if we look at my formal charges, you can see this is a 0. That's a good happy place. It's down here where we got the charges in the mess. So this is not equally good. That hydrogen makes it different. We would stop. There's 2 Lewis structures. And you're probably asking yourself, what does the composite look like? Let me get a marker that writes a little bit better. The composite looks like this, right? And this is where we get our little blurred dotted line, our partial negatives, that gets spread out, and that's what the real molecule looks like. If we were to do bond order on this, bond order across the top, oxygen, nitrogen, 1 and 1, 2 divided by 2, so there's a bond order of 1.0 here. If we look at this, 1, 2, 3, divided by 2 pictures, bond order of 1.5, 1, 2, 3, divided by 2, 1.5. So we would expect to see what? 2 shorter, stronger bonds, and then the one attached to the hydrogen is going to be longer and weaker. What if we had this picture? And I think you can see what the difference right away here is going to be. Now, if we take that hydrogen away, the double bond can go on any of the oxygens. They're going to be equally good. Again, we cannot move the molecule. So the atoms have to stay put. We can just slide the oxygen, or the double bond, sorry. And I suppose I should label this. And then, of course, we can go the other way. And we would have this. Now my question here is, how do these bonds compare to each other? So again, we'll do the same bond order calculation. Let's go vertical first. 1, 2, 3, 4. 4 bonds divided by 1, 2, 3 pictures gives me a bond order of 1.3, or 1 1/3. If I go down and left, 1, 2, 3, 4, divided by 3 pictures gives me a bond order of 1.33. And down and right, 1, 2, 3, 4, divided by 3 pictures gives me a bond order of 1 1/3. So in nitrate, I would expect the bond lengths to be identical, bond angles to be identical, bond strengths to be identical. I would also expect them to be slightly stronger than a single bond and slightly shorter than a single bond. And this is exactly what we see experimentally. So this allows us to continue to use the same theory and same knowledge and same talking points that we've been. This is called valence bond theory if you're curious. And just giving a little bit of a modifier with this idea of resonance. So again, in conclusion, if you're ever asked to interpret the picture, it's the average that matters. None of the individual pictures are right. The other thing, if you get anything else from this video, is you're moving around a double bond between equally good spots. That's when you have resonance. There you go. I know this is a little bit tricky, and I hope you enjoyed it. Continue to be fantabulous, and I look forward to seeing you in class.